Hello everyone, this project is going to focus on the simulation of the inverted pendulum, also how we can balance this unstable system using negative feedback control force. And this diagram shows the system schematic. The pendulum rod is able to swing freely on top of the control car, which are able to move back and forth freely for balancing the pendulum rod on the upright position. And for simplicity, we have a following assumption. All the experimental object has an evenly distributed mass. The pendulum rod is massless. There's no friction on the motion, meaning there's no loss in energy. And this is an equation that governing the system dynamics. And the details of how I derive those equations can be found on my research paper. And the simulation on the computation is based on the differences of equation, which we actually learned from previous assignment. This is the difference equation set, and this is the second derivative of the car displacement and the angular displacement of the rod. Here's the snapshot of my sample code, how I implemented in Python Jupyter Notebook. And this is a simulation result based on different initial angle. So when the starting angle is 0 degree, which is the pendulum rod is in the upright position, it is equilibrium position. So we experience no angular displacement and angular velocity. The car should stay still because the system's in the equilibrium position, and the result does show this behavior. We have nothing going on the time series. When the initial gain goes to 180 degrees, which is the other equilibrium position, we should also experience no change on angular displacement and position. And we does see that because as you can look at the scale, we have an extremely small scale. The whole thing is actually as around in 0. The reason why we have this line is because some of the combinational error, which is negligible. So when the initial angle is 10 degrees, we start seeing the oscillation of the pendulum. And the way we can have the model is correct is when the pendulum is at 180 degrees, the velocity of the swing is actually maximum. This makes sense for pendulum system, and the oscillation happens in the cycle. So meaning that the pendulum rod can actually went back to the starting angle and back and forth with no loss in energy. That's why we're seeing the peak repeat itself over and over again. And this is the same for the 90-degree cases. Because 90 degrees are bigger angles, we should see a higher frequency. The reason why this is the way it is can be found on my research paper. For the control of the inverted pendulum, we're going to use the negative feedback control forces. It's a PD controller, and the PD controller is based on the angular displacement and angular velocity. So we have a gain for each of these parameters. We have negative control force, mean that each have a different side of the rotation of the system. And this is the implementation in Python. And here's the result of the implementation. So as we increase the position gain, which is Ka, we increase our system balancing performance. As you can see, the balancing time is decreased from almost 15 seconds to around 12 seconds. As we increase more, we get even more performance gain. Now the balancing time is actually dropped back to around 6 seconds. Next, we're gonna further increase. We stop increasing the position gain. We increase the velocity gain, which is Kw, from 220 to 100. We experience even more performance gain on the balancing time. Now it's actually dropped back less than 2 seconds. As we increase even more from 200 to 400, from 100 to 200, the balancing time is less than 2 seconds, but that's about it. So if there's no gain if we increase the Kw even further. So the conclusion that the optimum gain should be around using this control gain will be have an optimal solution.